All right, so I kind of messed up and stopped that video a little short, but we're back to it. So negatively skewed means the mean is to the left of the mean and median. Positively skewed means the mean is to the right of the mean and mean and median, mode and median. Oh my God, okay. So let's talk about what variation is. Okay, so if you look here, this has 3 different graphs. And I know you guys know this, but I just want to go over it. The more variation there is in a population, the different the curve is going to look. So if you look at this green line, let me get a green pen. So this green line right here is really flat. So if you think about it, it's really spread out. So a lot of the population isn't falling at the mean. They're falling around the mean, right? But they're more towards, like, it's just spread out. Versus if we look at the red one right here, this one is really peaked and really high. And so that means that most of the population falls close to the mean. And if you notice, the standard deviation here is only 0.5 versus here it's 2. So the higher the standard deviation, the flatter the curve, I guess is one way to look at it. Okay, moving on. Oh, I just want you to remember to really look for variation in stats. The variation is where the cool stuff happens. I happen to love outliers. I think outliers are really interesting cases. And if you want to read a really good book, there's a book called Outliers. I think it's by Malcolm Gladwell, and it's looking at all the people that are just like amazing at things because they're outliers, they're experts. So anyways, all right, moving on. Okay, let's talk about inferential statistics. So this is where we infer. So can I take a sample of a population and then find some results and actually generalize that to the whole population? This will actually look at hypothesis testing. And there's lots of different tests. Those of you in AP stats have heard of some of these probably. The Z test, the F test, the T test, the ANOVA test, there's so many. And then there's also regression analysis. I think I took an entire graduate class on regression analysis. We do not need to know those. Like, you don't need to know how to calculate those for this class, but you do need to know when can you generalize. Okay, so when can you use inferential statistics? So the first thing you need to do is definitely random sampling, because if you don't have random sampling, your sample is biased and therefore you cannot infer. So the less variable your observations are, the stronger your inferences can be. So the basketball example is in your textbook. Imagine a basketball player and we're counting his scores for different games. And let's say that every game is very different. Well, I can't really use that to infer how well he's going to do in the next game or predict. But if my observations of his games are very similar, then it is better. And finally, the more cases, the better. So bigger sample size is always the way to go if you can. It does cost more money, but the key to remember about this is that generalizations based on a few unrepresentative cases are absolutely unreliable, and you cannot use them. Okay, moving on. Statistical significance. I think this one's kind of cool. In psychology, if you have never actually taken like AP biology or learned about what a p-value is, it's basically saying that there's a 5% chance. So a p-value of 0.05 is saying there's a 5% chance that what I'm seeing, this relationship I'm seeing, is due to random chance. Okay, so randomness. Now, some sciences use much smaller numbers. So obviously chemistry and physics aren't going to use 5% because that's a pretty big random chance for chemistry if you're making something like an atomic bomb. So how do we know that what we're seeing is significant? We're going to use something called standard error of the mean. So remember that I took a sample of a population. So this sample here, this bar indicates the average. So where this bar is the average. Same thing with this one. Notice these the bars on the top of each one. Okay, those are called standard error bars. If they overlap, like it's showing right here, then you cannot say that there is a statistical difference. Because what a standard error of the mean is saying is that somewhere within this bar right here is the true average for the population. The larger the bar, the less sure we are. So let me give you another example. Here is a graph about coping stress. So how well do certain groups cope with stress? Okay, so we have 4 groups. We have sedentary, so those are people that don't move very much. We have people who move only a little bit, people who are moderate movers, and people who are high movers. Okay, and then over here we have their ability to cope with stress. So I ask you a question, and I would say on this graph right here, can I say that all 4 of these groups are significantly different? So take a second, pause the video if you need to take some time to look at it. So if I were looking at this, I would say that I cannot, if I'm, that line was horrible. There we go. I would say that I cannot say there's a difference between sedentary and low, between low and moderate, and definitely not between moderate and high. But I can say that between moderate and high, there is a difference between these two groups because those bars don't overlap with the sedentary. I hope that makes sense. Basically, I'm saying the average ability to cope with stress for the moderate group falls somewhere within this bar. And so if it's overlapping with this low group, it's possible that the averages are the same. So I can't say that I did find a difference. I hope that makes sense, and we can talk about it more in class. So that is it for this video. I hope that all made sense, and I'll see you guys in class. Thanks.